Good afternoon. This is the lecture on section 3.5. This is the lecture on optimization. So let me share the slides here and get started. Okay, so optimization is shows up as an application of finding extrema. Mainly absolute extrema, but keep in mind sometimes absolute extrema occur where local extrema are. So the goal of mathematical optimization is basically, given a function, we're trying to find the maximum or minimum value of the function. The term optimization refers to either we're maximizing or minimizing in this context here. And so typically for an optimization problem, there are three components to it. There's the function that we're trying to optimize. There's what type of optimization are we trying to do, either maximize or minimize. And then there's typically a third condition given called a constraint. So this is a restriction that the equation we're trying to maximize or the function we're trying to maximize has to always satisfy. The optimization problems are typically real-world applications, and so traditionally there are some real-world restrictions on the math we're trying to do. So as I said, this is a absolute extrema problem. In every mathematical optimization problem, the goal is to find the absolute extrema, but we should keep in mind that it is possible for absolute extrema to occur at local extrema. So we will sometimes be using our local extrema techniques to find the absolute extrema. So the basic steps of optimization are as follows. First, one step is to determine the function to be optimized. So in every optimization problem, there's some function to be optimized. Then to determine whether this is a what type of optimization problem. So when we say optimization, we're either talking about maximizing or minimizing. And so here to define exactly what type of optimization problem are we trying to do. And then finally, the third component we need is the constraint equation. So the constraint equation allows us to, at least for a Calc 1 problem, is the final piece we need to put together a complete optimization problem. So from a technical point of view, the function we're trying to optimize typically involves more than one variable. And so here I say all the dependent variables plural. And this is really, a Calc 3 problem, technically speaking. But the constraint equation allows us to convert this from a Calc 3 problem to a Calc 1 problem. We're able to use the constraint equation to convert it from two variables into one variable. And so the third step, once we've assembled our optimization problem, once we've found the function, determined whether we're trying to maximize it or minimize it, and written down the constraint, we can then use the constraint equation to start solving the problem. And the first step is to convert the problem from a multivariable problem to a one variable problem. And once it's converted to a one variable problem, then it looks like any other type of extrema problem that we've done in section 3.1 or 3.3. Then we're just back to doing derivatives, finding critical points, classifying them. It's back to just a derivative problem. So yes, once we get it as a one variable problem, then we solve, the extrema problem using techniques we've learned. So in the optimization section, there is a new test here called the first derivative test for absolute extrema. So I want to mention that this is a test for finding absolute extrema that uses this shape. And so this is unusual. Traditionally, we find absolute extrema by calculating the y values at the endpoints and at the critical points. And traditionally, we find local extrema by analyzing the shape. If it's going up and then down, it's a local max. If it's going down and then up, it's a local min at a critical point. So here we have this kind of a unique situation here where we're going to use the shape to classify whether it's an absolute extrema or not. And this is a very artificial situation in which essentially there's only one high point in the interior of the domain, or there's only one low point in the interior of the domain. So in this case, the one high point is a local max, but because of the geometry, it is also an absolute max. And similarly with the case where you have only one low point in the entirety of the function. So here, it says here, if f prime of x is greater than 0 for all x less than c, that is to say, if the function is increasing for all values of x less than c, here c is a critical number, and if f prime of x is less than 0 for all x greater than c, so that means it's decreasing for all values of x after c. So before the critical point, the function is only increasing, and the key phrase I want to emphasize here is this says for all x in the entire domain. So if before the critical point, the function is always only increasing, and after the critical point, the function is always only decreasing, then, you know, obviously we have a local max here, but it's also an absolute max. And you have a picture like this where there's essentially, this is only works when there's one critical point like this in the interior, and then, you know, you have to the left, the function is increasing, to the right, the function is always decreasing. It's kind of a very artificial situation. And if you flip this picture upside down, we get the other criterion. Again, if we have the function decreasing for all x to the left of the critical point, and then the function is increasing for all x to the right of the critical point, if we think about it, it's, you know, if it's always decreasing to the left and always increasing to the right, then at the critical point, that obviously that's a local min, but it's also the lowest point. It's also the absolute min. And so, as I said, we have this picture that is, to me, a bit of an artificial situation. It's when, you know, you only have this one critical point in the interior. But certainly this scenario will show up, you know, time and time again in some of the homework problems. And the book will use this first derivative test for absolute extrema. As I said, this is a bit unusual. Traditionally, most calculus books will not have a first derivative test for absolute extrema because we classify absolute extrema by classifying the shape. But as I said, in these unique situations, we can use the shape to classify the absolute extrema. So here, I wanted to start, you know, with kind of an easy problem and then slowly make them harder and harder. So here is an optimization problem. The number one comment I would make here is when I'm reading the question, so it says, what is the largest possible area for a right triangle whose hypotenuse is 5 centimeters long? So when they say what is the largest possible area, this phrase here, the largest, that tells me this is an optimization problem. An optimization problem in Calc 1 is always looking for extremes. What's the largest? What's the smallest? What's the most? What's the least? What's the greatest? What's the, you know, so that's a kind of key word for me. When I say what's the largest, I say, aha, this is an optimization problem, as opposed to a related rates problem. The other thing about an optimization problem I want to point out is this is fixed in time. The triangle here is not growing or shrinking, it's fixed. And that's drastically different from a related rates problem. In a related rates problem, as you know, everything is moving in time, and time is kind of a hidden variable. It's a parameter. Here, that's not the case. So here, I know this is the type of optimization problem where we're trying to find a maximum. The function that we're trying to maximize is the area of this triangle. And the constraint, the restriction that must always be true is specified here. It says that the hypotenuse has to always be 5 centimeters long. So here, we're looking at the area of a triangle where the length of the hypotenuse is fixed, and that's our restriction. So these are the three pieces of information I need to formulate the optimization problem. So in the diagram, I have a triangle, and I've labeled the length of the base to be x, I've labeled the height to be y, And so I can formulate the optimization problem in this way. So here we're going to maximize the area of the triangle, and the area of a triangle is given by 1/2 base times height. Here the base is x and the height is y. So I'm trying to maximize the formula a of xy equals 1/2 xy. So I want you to notice this is a multivariate function, that there's two variables here. So, you know, from a formal point of view, from a mathematical point of view, what's going on here is we're in 3 dimensions here. In Calc 3, we would label this function as z equals xy. And now the domain is a 3D domain where in the plane here, in the base, we have an x and y coordinate. And then coming out up off the floor, we have our z coordinate. And z equal to 1/2 xy can be interpreted as what's called a surface. It wouldn't be a function. So I'm going to draw a simple kind of surface here that looks like a hemispherical dome, maybe. So there's the surface. And essentially in this optimization problem, we're trying to find the highest point on the surface. Specifically here, you know, we'd like to know what are the x and y values that take us to that high point. You know, the drawing wasn't great, not the greatest. So this is a Calc 3 problem that you'll learn how to solve, but in Calc 1, we will use the constraint to make this a Calc 1 problem that you can solve. So once we introduce the constraint, which is that x squared plus y squared equals 5 squared. So this part's important to realize that we've translated this English sentence that the hypotenuse has to be 5 centimeters long. This is the equivalent mathematical sentence. And translating from the, you know, the English sentence to the mathematical sentence sometimes can be a little tricky. But that's how we enforce that the hypotenuse has to be 5 centimeters long, by requiring x squared plus y squared equals 5 squared. So this is the official formulation of the optimization problem. When someone says I have an optimization problem, this is what we're looking for. That the function to be optimized, whether we're maximizing it or minimizing it, and what's the constraint, what's the restriction. So now, to me, this is the tricky part. Now, the rest of it to me is a little bit plug and chug. We're now just going to convert this into a 1 variable problem. So using the constraint, I can solve for y. So here y squared equals 5 squared minus x squared. So y equals plus or minus square root of 25 minus x squared. So technically speaking, the mathematical solution is plus or minus. But because this is an applied problem and because y represents the height of the triangle, y cannot be negative. So here I'm only taking the positive root. And again here, x is required to be greater than or equal to 0 since x is a measurement, a length measurement. And x is required to be less than or equal to 5 because of the domain restriction here from taking the positive root of 25 minus x squared. We don't want to take the even root of a negative number. So once I plug in this expression for y into our area formula, we will get a function that's completely in 1 variable. And now this converts into a traditional type of extrema problem that we've solved in section 3.1 for absolute extrema or in section 3.3 for local extrema. So now I'm going to solve this problem using one of those techniques. So I'll actually use this first derivative test for absolute extrema that's been introduced. But here you could absolutely use the closed interval method. And I mean, you know, traditionally that's what we would use here, given the setup, because we're given a closed interval. But let's try their first derivative test for absolute extrema, just to get used to it. So of course, the first step is to take a derivative, right? Everything in this class boils down to a limit, a derivative, or an integral. Here, when you're taking the derivative, I want you to realize it's a product, so we must use the product rule. The first function here is 1/2 times x. The derivative there, the derivative of x is 1 times the second function. And now for the derivative of the positive square root of 25 minus x squared, that's a composition, we need a chain rule. And so I'm going to copy down the first function multiplied by the derivative of the second function, where this is a chain rule, derivative of the outside times the derivative of the inside. So now we're done with the calculus part. So this next part is very important. We must realize that there's a fraction here in the second term. And so we can combine this. So what happens here is that this term will go down in the denominator with the 2. And in the numerator, this 2 here will cancel with the 1/2 we had here. And you'll get an x times an x with a minus sign. So our second term looks like minus x squared over 2 times the positive square root of 25 minus x squared. So what I'm going to do is multiply top and bottom here by 25 minus x squared to the 1/2. I already have a 2 in the denominator, so I don't need to also include the 2. I just need to multiply by the 25 minus x squared to the 1/2 top and bottom. The numerator becomes 25 minus x squared to the 1/2 times 25 minus x squared to the 1/2 is 25 minus x squared. And then minus, the other term is minus x squared. So eventually when we combine everything, we get 25 minus 2x squared over 2 times the positive square root of 25 minus x squared. So that's our derivative as a single term. And as you know, a fraction is 0. So now we're looking for the critical point. So I want to know where the derivative is 0 and undefined. A fraction is 0 when the numerator is 0. So here, if I set 25 minus 2x squared equal to 0, here, this equation will equal 0 when x squared equals 25 over 2. And the solution to x squared equals 25 over 2 is x equals plus or minus the square root of 25 over 2. And the square root of 25 is 5, so x equals plus or minus 5 over root 2. And now, since x represents a length measurement, I get rid of the negative root. So here's one critical point. And here, 5 over root 2, since root 2 is larger than 1, 5 over root 2 is less than 5. This is in the domain. Here, the function is undefined when the denominator is 0. And so we can see the denominator will be 0 when x equals plus or minus 5. But of course, minus 5 is not in the domain. And we can check that at 5, the derivative, if you take the limit, for example, the derivative blows up. Or you could say 5 makes the denominator 0, but not the numerator. And so in that case, the limit would also go up. And so we can conclude we have 2 critical points. Now, if I check 5 as a critical point, if you just plug it in, you see that the area will be 0. Or we can not even plug anything. We can just look at the shape behavior of this function in its domain. So I'm going to put a number line. I'm going to indicate the domain. So here from 0 to 5, and just check the derivative. Check the sign, S-I-G-N, of the derivative. Here, if I plug in, so for example, if you put x equal to 1, and remember now we're plugging it into the derivative. So I'm plugging it in to the derivative. If you plug in x equal to 1, numerator and denominator are positive, the function is increasing between 0 and 5 over root 2. That piece of information by itself doesn't tell us anything, but to the left of 5 over root 2, the function is always increasing, And to the right of 5 over root 2, so for example, you could pick 4.9. Here, when we do 4.9 squared, because 4.9 is less than 5, 4.9 squared is going to be a number less than 25. And so here, 2 times, you can even use 4, right? 4 squared is 16. 2 times 16 is like 32. 25 minus 32. You see the numerator will be negative here. The denominator is always positive. The derivative is negative. And so just based on the shape, without the graph, here we have that the function is always increasing to the left of 5 over root 2 and always decreasing after 5 over root 2. So not only do we have a local max at 5 over root 2 in this case, but because there's just one critical point here, we also have an absolute max based on the geometry. As I said, this is unusual to use the shape to classify an absolute extrema. And we must answer the question asked, what is the largest possible area? So now I'm going to take x equal to 5 over root 2 and plug it in to this area function. And then calculate the numbers. We get 25 over 4 centimeters squared. So that would be the largest area of a right triangle where the hypotenuse is fixed at, a length of 5 centimeters. Optimization problems are important from a manufacturing standpoint because we want to know exactly how much material we're using when we build something. So optimization allows us to analyze those types of details so we can plan ahead for our resources. We never want to buy too much or buy, not enough. Ultimately, we don't just want to solve problems or do engineering. We want to do those things as efficiently as possible, in terms of saving our resources. So this next problem is a little more complicated than the previous problem, but the idea is that, hopefully you'll start to see the pattern of what's happening here, the thought process. So it says, consider the rectangle inscribed in an isosceles triangle as shown. So here's the rectangle and it's inscribed. What that means is its corners have to, this one corner has to be on this one side of the triangle and this other corner has to be on that triangle. And then you see the base here. So there's my rectangle inscribed in the triangle. The question says, what is the largest area the rectangle can have? So what I notice is this phrase right here, what's the largest? So that tells me this is an optimization problem. We're trying to optimize the area of the rectangle. And what's the constraint? The constraint is that the rectangle has to be inscribed in the isosceles triangle. So the question now is, how do we convert this into a mathematical statement, first of all? Remember that part of the problem is writing down what the problem is. So I'm not even going to try and solve this yet. I'm first going to try and formulate the problem, and then I'll try and solve it. So let's start doing some math. What I notice is that, if I label the rectangle in this way, where I'm calling this distance from 0 to this right edge x, so here x is a positive number, and then the height is y, so this point is xy. What I'm noticing is that the y coordinate is on this line. So let me find the equation of this line, and certainly you could do all this analysis with the other line as well. Let me find the equation of the line that goes to the point 1, 0, 0, 1. Here I can find the slope and do point slope form. Or of course you could just imagine it's just the line negative x where we've shifted up 1. So here, the equation of that line is y equal to negative x plus 1 with the domain restriction of x being between 0 and 1. And so now we can use this to formulate both the area of the rectangle as well as the restriction, okay? So first of all, the area of a rectangle is base times height. So here, for the base here, if I'm calling this distance from 0 to x, so here x is a fixed positive number here, x, then the entire distance will be 2x. Or another way to think about it, if this is x where x is positive, this is a fixed x where x is positive, then this would be negative x. And the way we calculate the width would be right minus left. And so x minus minus x, we get the base of our rectangle is 2x. And the height of our rectangle is y, this distance. And so I can formulate, and this is a maximization problem, so I can formulate the optimization problem in terms of the function and how we're optimizing it in the following way, that we're trying to maximize the area, which is 2x times y. And now we need to force the rectangle to be inscribed. And so this is the part where we use the equation line. I'm going to now force this y coordinate here to be on this line. I'm going to force the y value to be the output of this line. So here's the restraint, the constraint that we require y to equal 1 minus x, where x is between 0 and 1. So what that says is, for any x value here between 0 and 1, the y value will always be on this line. And then, you know, we'll get a corresponding rectangle depending on where along the line we are. And that's a terrible rectangle, but you know, we're trying to find the rectangle here of largest area. Which one of these, where you can move that y point anywhere along that diagonal line. So yeah, to me, this is the tricky part of an optimization problem. Once we've formulated the optimization problem, the rest is plug and chug. So what's going to happen now? Well, this y variable here will be replaced with 1 minus x. Then the function becomes a univariate one variable function, and we're just back to finding extrema in the usual way. So here, I now want to find the absolute maximum of this function here, 2x times y, or 2x times 1 minus x, where x has to be between 0 and 1. And this looks like now a very traditional absolute extrema problem. And again, I'm just going to use their, you know, first derivative test for absolute extrema thing that they've introduced in section 3.4, they being the authors of our textbook. So here, for the derivative, rather than do a product rule, it's easier for me to distribute here and then get 2x minus x squared, and then just take the derivative of each. So the derivative of 2x is 2, the derivative of 2x squared is 2 times 2x, or 4x. And so now set the derivative equal to 0, and we see x, the derivative is 0, and x is equal to 1/2. 1/2 is in the domain, so that's a critical point. The derivative has no denominators, so this is the only critical point. And so now we need to classify. We could try the closed, you know, we could use the closed interval method, plug in the endpoints and the critical point into the function and pick the largest value. Or in this case, let's analyze the shape and see if we can say anything. Here, if you look at a chart for the derivative, we can show that before, to the left of the critical point, 1/2, the function's always increasing. So here, 1/4, I plug into the derivative. So yeah, 2 minus 4 times 1/4 will be 2 minus 1, which is positive. Check. And plug in like a 3/4 here into here. So that'd be 2 minus 4 times 3/4, 2 minus 3, which is a -1. So based on this geometry, yeah, we have a local max at 1/2, but obviously it has to also be an absolute max because, you know, there's no other option here. So we have a local max at 1/2, which gives us the absolute max of this function. And so the largest possible area, which is what the question originally asked for the inscribed rectangle, I'm not going to take the 1/2 and plug this 1/2 into the area function. This time I'll get it right. Yeah, here we are actually plugging it to the original area function to find the absolute maximum area here for the inscribed rectangle. So yeah, that's the whole procedure. And I feel like the slide before this is the tricky slide where we have to set up the problem. This slide is mostly plug and chug. And a lot of these problems will typically only have one critical point, and then you just classify it. You know? So here is yet a more complicated problem, right? I just want to make these harder and harder. So what are the dimensions of an open top cylindrical can that will hold 1,000 centimeters cubed and requires the least amount of material to construct? So we should read the question a couple of times and think about the units and then go through this very slowly. The first thing I'm going to say to you is this word least tells me this is an optimization problem. We're trying to minimize something. Then it says least amount of material to construct. So if I'm building this cylindrical can, I'd first start out with flat sheets of metal and then shape the metal. So here we're trying to find the least amount of surface area because I have a flat sheet of metal, the sheets of metal that's measured in area. So minimize the surface area of an open top cylindrical can that will hold 1,000 centimeters cubed. So what's the constraint? There are two constraints here. One constraint is that this can does not have a top. It's an open top cylindrical can. So here in the diagram, this part of the diagram, we don't have any material here at the top part. It's hard to line up. Let me try. Oh yeah, that top part, there's no material. It's open. It's like a waste paper basket. So we only need surface area. We only need material for constructing this thing around the sides here and the bottom. Okay. And the other constraint is that it has to hold 1,000 centimeters cubed. So here's where units are important. Centimeters cubed tells me that that's volume. So here we want to minimize this open topped cylindrical shape, and the constraint is the volume has to be exactly equal to 1,000 centimeters cubed. So here are three parts of our optimization problem. So if I let, in this diagram, let R be the radius and let H be the height, then we need the volume to be 1,000 centimeters squared. And as you know, the way we find the volume of something like this where the cross section is identical, we can just find the area of the base and then multiply that by the height. Right? It's basically what we call the loaf of bread method, where you have a loaf of bread. To find the volume, you can just find the area of one piece of the face of the bread and then multiply it by the length of the loaf. And that's your volume of the loaf of bread. So here we find the volume of the cylindrical can should be, so the area of the base is pi r squared times h, and we set it equal to 1,000. So here, pi r squared is the area of the base times the height, so that's the volume, and we set it equal exactly to 1,000. And this is one of our restrictions. The other restriction is there is no top. So this is going to factor into when we write down our formula for the surface area. So this is the area of amount of material that we'll use to make the can. So for the surface area, let's take this very slowly. We have the bottom surface, which is a circle. And so for that, the area there is pi r squared, and there's just one. So this is where the constraint is coming into play. I don't say 2 pi r squared. If it had a top, if we were also including this top part here, then it would be 2 pi r squared, but that part, is open. And then we need the material for the sides. So it's a little bit tricky, but the way to think about it is assume it doesn't have a bottom. So we've gotten rid of the bottom. Take the side here, cut it, and flatten it. If you cut it along its side and flatten it, it'll turn out to have a rectangular shape, right? If I connect this end to this end, that's how I get my circular cylinder. So now let me find the area of this. So we know this rectangular shape. We know the height here is given as h. So the height here is given as h. The height is h. So, and now I need the width. The width here coincides, if you look, coincides with the circumference if we go all the way around. So the width coincides with the circumference, and the circumference is 2 pi r. So the area of the side here, if we do width times height, would be 2 pi r times h, or 2 pi r h, and that's where this second term is coming from. And so here's the optimization problem. I want to minimize the amount of material required to construct this open top cylindrical can. We require pi r squared for the base, and for the sides we need 2 pi r h. And the restriction is that the volume has to always equal 1,000. So once we've formulated the optimization problem in this way, to me, this is the trickiest part. The rest of this will now be plug and chug. So what we should notice is that in the function we're trying to optimize, minimize, there's two variables, r and h. So what we will do is we will use the constraint equation to solve for one variable in terms of the other, and then convert the function we're optimizing into a one variable function, and then find the critical points, and it's all the usual stuff. So here, I solve for h in terms of r. Why? Because if I solve for r squared, that gets a little bit messy and annoying. R squared would equal plus minus the square root of 1,000 over pi h, and I drop the negative root. So r would be the positive square root of 1,000 over pi h, and that's kind of irritating to differentiate. It's much easier to solve for h. H here is just 1,000 over pi r squared, so I solve for h. And so now substitute this expression for h. So replacing h, we get this one variable function completely in terms of the radius r that represents the surface area required to construct the open top cylindrical can that'll have a volume of 1,000 centimeters cubed. That's built in now, that the volume will be 1,000 centimeters cubed because we've applied the constraint. So now it becomes a traditional, oh, and here, by the way, here, the domain over which we're optimizing is r greater than 0. So this is, think about this mathematically. This is 0 to infinity. So for checking endpoints, we would take a limit. And you can see here, if you take a limit, you'll see on the next slide, if you do take limits, the function we're trying to optimize blows up. You know, we have a denominator here that'll go to 0. Otherwise, we have a polynomial when we send r to 0, this term with the denominator will blow up. Otherwise, we have this polynomial term here, r squared, which will blow up when you go to infinity. So here, you know, the extrema is going to occur inside the domain. This is, you can still think of this as an absolute extrema problem. We would check the endpoints with a limit, which is kind of what I did roughly. But here, you know, it's going to look like the point we're looking for will occur internally, because on the endpoints, things aren't minimizing, they're exploding. So here's the function. You think about here, the domain is 0 to infinity. And if you take a limit here, and I canceled the r squared and the r, I simplified it. You'll see that, you know, the endpoints aren't really going to work out. So here, anyway, I need to find the critical points. So I write 2,000 over r as 2,000 times r to the minus 1. And so this is a sum. You can just take the derivative of each part. So derivative of r squared is 2r times the pi, I get 2 pi r. The derivative of r to the minus 1, that's a power rule. Bring the minus 1 down. So that's where this minus sign comes from. And then that's where this sign comes from. And then r to the negative 2. So that's where this 1 over r squared comes from after the derivative. And so now I combine everything into a single fraction. So I'm going to multiply this term top and bottom by r squared over r squared. And so combine the fraction, it looks like that. And so now we want to find the critical points. So now I want to know where's the derivative 0 and undefined. We know that it'll be 0 when the numerator is 0. So it'll be 0 when r cubed equals 2,000 over pi, 2 pi, or 1,000 over pi, or r is equal to the cube root of 1,000 over pi. And the cube root of 1,000 is 10. So I write this as 10 over the cube root of pi. Certainly, that's positive, and so it's in our domain. And the denominator is undefined at 0. And so that would be part of our domain, but you'll see that when we do the shape analysis, we'll see that it's not possible for the answer to be at 0. Another way to see this, like I said, is to take a limit, and you'll see the answer is not possible. But let's just look at the shape behavior. So here we're in our domain 0 to infinity, and to the left of 10 over the cube root of pi, this function is negative. So for example, pick 1, you know, pick something small, pick 1. So take that and plug it into, let me get this right, the derivative. So I'm actually going to plug it into this version of the derivative. Plug in a 1, yeah, you get 2 pi minus 2,000, yeah, that's negative. And then on the other side, for example, you could just take 10 if you want. 10 will be bigger than 10 over, the cube root of pi, because cube root of pi is bigger than 1. I'll let you think about why all those statements are true. So if you take 10 and stick it in there, then you get like 20 times pi, which is like 600 minus 2,000 divided by 100, which is like 20. So that's positive. That's going to be positive. So just based on the shape, because it's always decreasing to the left of 10 over cube root of pi and always increasing, not only is there a local min there, it must also be an absolute min. It must, just based on the geometry. And so now, we can find the dimensions required. So we also have to find the height. So the problem asks for the radius and height here. We found the radius. To find the height, I just go back to the formula that we get from the volume. So the volume formula, volume having to equal 1,000, tells us h is equal to 1,000 over pi r squared. So I replace r with 10 over pi to the 1/3. 10 squared is 100. Pi to the 1/3 squared is pi to the 2/3. And, when we dividing by 100 over pi to the 2/3 is the same as multiplying by the reciprocal. And so now if you do some cancellation, just by coincidence, you get h is the same 10 over pi to the 1/3. It turns out to be the same as the radius. So that was a tricky problem. The setup, I think, is a little more tricky. A little bit, the math is a little bit messy, but this is a very traditional type of optimization problem. This is very traditional. So it starts with finding the function you're trying to optimize, determine what type of optimization you're doing, maximizing or minimizing, and then finding the constraint equation. And of course, writing all of these things mathematically is the trick. Then using the constraint equation to go from a multivariable problem to a one variable problem. And then you're finding extrema in the usual way. You're finding the critical points and you're trying to classify the critical points and the endpoints. Depending on the situation, you can just look at the shape and determine if it's an absolute extrema or not. So here's a slightly more mathy technical one. There's a little trick here in this problem that I wanted to show you. So here we want to find the point on the curve y equal to square root of x that is closest to the point 1/2 16. So 1/2 16 is a point that's not on the positive square root. Okay, so we're trying to find a point on this curve that's closest. I would guess it would be somewhere right here, right? So we're trying to now find the coordinate of this point. Okay, so there's a little trick here that I want to show you. So yeah, we're trying to minimize the distance. So in terms of classifying, the optimization parts, we're trying to minimize the distance, and the requirement, the constraint will be that this point, the distance between 1/2 16 and the point xy, that point xy live on the curve. So here, let's formulate the optimization problem. The distance formula, I don't know if you remember the distance formula, but you take the difference of the x coordinates and square them and add it to the difference of the y coordinates squared and take the positive square root. It's basically the Pythagorean theorem, and we're calculating the length of the hypotenuse, because there's a triangle here. And we're just calculating the length of the hypotenuse. There's a right triangle right here. So this is the function we want to minimize. And the restraint, here's the restriction, where xy, so this y coordinate here, has to satisfy this equation. The y coordinate has to, be equal to square root of x, so that the point xy is always on the positive square root of x curve. So here's the optimization problem. Minimize the distance formula subject to y equal to square root of x, x greater than or equal to 0. So we could proceed as usual. So I could replace this y, I could replace this y with square root of x, and then try to find the derivative and do all of that mess, okay? The one thing about this problem, though, is this function, the square root of all this junk, is really messy to differentiate. And then you'll have a square root inside the square root. That's going to be really horrible. So here's a trick that's really useful. The square root, the positive square root function, and I'm referring to this part of it, okay? So careful. I'm referring to this positive square root here, not this function. Okay, this positive square root function here is an increasing function. Yeah, I know every positive square root function is increasing, but I'm referring specifically to when it appears here. That positive square root function right there is an increasing function. So what does that mean? You can minimize or maximize the thing under the square root function by minimizing or maximizing the thing under the square root. You know, if you look here at the graph, you know, if you move to the left, if you make the input large, the function gets large. And if you move to the left, if you make the input small, the function gets small. So I can minimize this root function by minimizing the stuff under the root. Because when that's very small, the square root will be of that small thing will be small. And when that's very big, the square root of that big thing will itself also be big. So here, rather than minimizing the square root of all that junk, I'm going to minimize the stuff under the junk under the square root. So if I want to minimize the positive square root of g of xy, I can just directly minimize the function g of xy. In this case, our function would be just x minus 1/2 squared plus y minus 16 squared. So here's my new optimization problem that when I solve this will simultaneously also be a solution to the original optimization problem because of the geometry of the square root function, particularly the square root that's appearing right here. So rather than work with this function, root of g of xy, let's just work with the thing under the root. So now this problem becomes a lot easier. Once you plug in, you get this thing that looks like a polynomial. You can directly take the derivative with the chain rule. And here, I first simplify by distributing this 2 and distributing this term as well as the 2. So when you do all of that math, you get this. And here, the 1's cancel, -1 and the 1. 16x to the minus 1/2, this is really a fraction, so I write it in fractional form, combine everything. And so now this is the derivative, and I want to know where the derivative is 0 and where the derivative is undefined. So the derivative will be 0 in the numerator 0. The numerator 0 is when x is equal to 4. And the derivative is undefined when the denominator is 0. The denominator 0 is when x is equal to 0. And finally, once I find the critical points, I want to classify them. Again, we could use, more traditional techniques. We could check the values and check limits to find the values at the endpoints. At 0, there's no problem. At the other endpoint, we would use a limit. But here, if you look at basically look at the graph, if we look at the shape behavior, we see the function's always increasing to the left of the critical point, always decreasing, and then always increasing. So yeah, we have a local min there, but based on this geometry, it's also an absolute min. And so the distance is minimized when x equals 4. And so the question was asking, what's the point on the curve? I need the x and y coordinate on the curve. So when x is equal to 4, y will be equal to root of 4 or 2. So the point on the curve, y equal to the positive square root of x, that is closest to 1/2 16 would be the point 4, 2. So every problem kind of has this pattern, right? There's always a function that we're trying to optimize. Remember, optimizing means minimizing or maximizing, and I'm looking for those those clear phrases. What's the largest? What's the smallest? what's the greatest, what's the least. And then there's always a restriction. And the trick now is to formulate the problem mathematically. And once you have those things, you can use the constraint to reduce the function into a one variable problem and then find the extrema in the usual way. So this is a little bit tricky initially, but the more you can practice with it, the better it gets, and optimization is very important. You'll see it again in Calc 3. So this ends the optimization lecture. So I just want to thank you for your time, and maybe watch the lecture again. All right, thanks everybody, take care.